I'd like to talk a little bit about Pythagorean triples. We did discuss this a little bit in class. I want to kind of come back to that idea. Before I get started with Pythagorean triples, I want to make the point here. This does not entirely replace the Pythagorean theorem. These are special cases. In certain cases, they'll give you really quick ways to be able to solve Pythagorean theorem problems, but you are still going to have to use the Pythagorean theorem in some cases. And in fact, if you never learned Pythagorean triples, you actually always could still use the Pythagorean theorem. But this will give you a quicker way to be able to do some mental math and not have to use the Pythagorean theorem in every single case. All right? The idea is very simple. Pythagorean triples are generally thought of as whole number values, I guess integer values, non-decimal values that work in the Pythagorean theorem. Okay? And there are a couple of cases that are really common. There are infinitely many of these, but some are more typical than others. The most common is 3, 4, 5. Okay? 3 squared plus 4 squared is equal to 5 squared if you put it into the Pythagorean theorem. So 3, 4, 5 right triangles are super common. Okay? 5, 12, and 13. Those numbers also work in the Pythagorean theorem. 7, 24, 25. 8, 15, 17. Okay, those are all whole number values that work in the Pythagorean theorem. Okay, the key here is any dilation of these triangles will create more Pythagorean triples. So for example, if I double 3, 4, and 5, I get 6, 8, and 10. Those would be side lengths of a right triangle. Okay, if I multiply these by 5, I get 15, 20, 25. Those are sides of a right triangle. Okay, if I triple these side lengths here, I get 24, 45, 51. Okay, you can multiply them by any value. You can divide them by any value. I can do 3 halves, 4 divided by 2 is 2, and 5 halves. Okay, shrink it down and get a smaller triangle. And so this is going to give us a way sometimes when you have whole number values to find Pythagorean theorem values, basically sides of right triangles, a little bit more quickly. All right, so let's take a look here at a few examples. So this is your pretty typical type of example that you're going to see. What you try to do here is, if it's going to be a triple, you have to see what that triple got multiplied by. Okay, the term we use here, we say that these numbers are relatively prime. What relatively prime means is, prime numbers normally don't have any factors in common other than 1 and themselves. So for example, 7 is prime because only 1 and 7 goes into 7. Okay, 8 is not prime because 2 will also go in, 4 will also go in. If you notice here, 4 is not a prime number. However, we can say that the numbers 3, 4, and 5 are relatively prime. They're prime in relationship to each other. In other words, there's nothing other than 1 that divides in all of these values. Okay, so notice there's nothing other than 1 that divides into 5, 12, and 13, or 7, 24, 25, or 8, 15, 17. Okay, these are what are generally referred to as the parent Pythagorean triples. Okay, they're kind of the basic ones that everything comes out from. So if you can find anything that will divide into side lengths of triangles, you might be able to shrink it down to a Pythagorean triple. All right, so take a look here. You're looking for the greatest common factor. What divides into both 9 and 15? 3 divides into both 9 and 15. 9 divided by 3 is 3. 15 divided by 3 is 5. Okay, this is coming from a little 3, 4, 5 right triangle. Make sure that that 5 side is the hypotenuse side. Okay, if I've got a leg that's 5 units, this is not a 3, 4, 5 right triangle. But this is a 3, 4, 5 pattern that got tripled. 3 times 3 is 9, 5 times 3 is 15, 4 times 3 is 12. That's your missing side. Okay, I didn't actually have to put it in the Pythagorean theorem. If I didn't notice that, I can still use the Pythagorean theorem. I could do 9 squared plus x squared equals 15 squared. You're totally going to still get 12. But this can be a little bit faster if you spot the triple. Okay? Second one here. Notice what divides into both 10 and 24. They're both even. So 2 divides into both of those. 2 goes into 10 5 times. Goes into 24 12 times. That would be a little 5, 12, 13 right triangle. It was a 5, 12, 13 that was being doubled. Okay, so 5 doubled is 10, 12 doubled is 24, 13 doubled is 26. That's your missing side. Okay, this one down here, 3 divides into both of these. 3 goes into 24 8 times, 3 goes into 45 15 times. This little 8, 15, 17 pattern that it was being tripled. Okay, you might not know 17 times 3 off the top of your head. However, it ends up being 51. And I think that was actually one I mentioned a little bit earlier than there. So that can be really useful. Okay, now you can get weird stuff too. You can get big things. You know, I could have 50, 120, and 130, just things that are multiplied by larger numbers. You can also have weird things like radicals. So for example, I could have a right triangle with side lengths of, you know, something like 6 radical 2, 10 radical 2, and I'm trying to find the missing side. And if you notice, 2 goes into both of these. The square root of 2 can be divided out of both of those, okay? And if I divide this by 2 and the square root of 2, I'd be left with 3. If I divide that by 2 radical 2, I'd be left with 5. It's a little 3, 4, 5 pattern that got multiplied by 2 radical 2. So if I multiply 4 by 2 radical 2, we get a side length of 8 radical 2 there, and that would be my missing side. So even in some strange cases like that, or you might have something like 3 pi, 4 pi, and 5 pi, each of the values getting multiplied by pi. You can see some strange things like that. It still works, all right? There is one other idea. This is not 100% required, but if you're working without a calculator, it might help some of you. If you've got sides that you don't think fit any particular triple, you still may be able to do things kind of similarly. For example, 18 divides into 36 twice. 18 divides into 54 3 times. Okay? There is no Pythagorean triple with legs of 2 and 3. However, 2 and 3 are easier to work with than 36 and 54 if you're trying to do this problem by hand or if you're trying to do it quickly. Okay? So according to the Pythagorean theorem, 2 squared plus 3 squared would be equal to, we can call that side x squared. That's 4 plus 9 is 13 equals x squared. X would be equal to the square root of 13. Okay? So basically I just made up a triple. Okay? It's not really a Pythagorean triple because it's not a whole number value there, but the point is that triangle could be dilated to give me this triangle right here. Okay? We multiply this by 18 to get this side, we multiply this by 18 to get that side, we can multiply radical 13 by 18 to get that side. We can get 18 radical 13, and that's your missing side, okay? That'd be a pretty tough problem to do by hand. So for some of you, that idea may help. Your book calls this the principle of the reduced triangle. Okay, not necessary, but it is a little trick that might help some of you.